this episode of Chem vs. Wild, we go up against the outbacks of Pittsburgh.
Given this climate and the humidity here, I reckon we're going to have to drink about a gallon of water or so a day in order to avoid dehydration. And on that note, let's go and find some water.
Do you hear that? I think it's water.
I think you're right. Let's go towards it. Yeah, that's definitely water, all right. And it's even better, I think it's clear. I think we just have to go and get it, right?
Yep, let's go.
You got the water?
Yep, I'm getting it.
That seems a little dirty.
Yeah, it is. Looks like we're gonna have to use some separation technique.
All right, so what could we use right now? I mean, it's not like we have a centrifuge.
Yeah, we could use a method called decanting, where we utilize the density of water and its impurities.
All right, so the water being less dense would float to the top, and then the impurities would be at the bottom?
Yep, that's pretty much how it works. We just have to let it sit and let it do its magic.
Then what else could we use?
We could also use filtration, where we lay a shirt or sock out and pour the water through it and capture the water at the bottom. It'll take most of the impurities out.
Okay, so how does that work?
The shirt or sock would capture the impurities, since the impurities are bigger than a molecule of water.
All right. Yeah, I think we're good. Here, let's go back to our base.
Yep, now that we have our water, we can head out.
All right, Alex, we got the water. I guess we can now go and make some food.
Yeah, we're gonna need some for tonight.
All right, so you know what the interesting part about boiling water is, right?
What?
So depending on where you are in the world and how high you are, water's gonna boil at a different temperature. You know why?
Why?
All right, so there's this thing called vapor pressure, and essentially that's the temperature that the water molecule is going to have to be, or any molecule for that matter, to boil, depending on the atmospheric pressure around it. So imagine that these are my two water molecules, right? So
Yeah.
in normal circumstances, when water is a liquid at room temperature, given regular atmospheric pressure, 14.7 psi or 760 millimeters of mercury, it's going to be like this, right? Assume my hand is the atmosphere. It's going to hold the water molecules like this. And as soon as we start to heat up the water molecules, they're going to start to move and they're going to start to separate. And after a point, they're going to be able to overcome the atmospheric pressure and they're going to become a gas. But the higher we go, the less of an atmospheric pressure there are. So instead of my hand holding the water molecules as tightly, now they're already kind of loose. So we don't even have to heat it up that much. So if you're on Mount Everest, then you're only going to have to heat it up 15 or 20 degrees Celsius. But right now, I mean, we really don't have to worry about it. Wow. Because we're around 1,150 feet in the air, or above sea level. So for us, it's actually not going to boil at a perfect 100 degrees Celsius, but rather at around 98 degrees Celsius if we calculate it.
So it's gonna boil at a lower temperature, thus making it easier.
Yeah, but the problem with that is that if it boils too low, then we won't actually be able to cook our food.
Oh,
So
good point.
we have to overcome that by using some type of method that allows the water to reach the desired temperature.
Ah, nature. Wait a minute, is that civilization I see?
I think it is. Let's go towards it.
Yeah.
At last.
We survived!
Water!